cubes.
Welcome back everyone for the next part of the Cubane series. It's been a while since the last video and a lot has happened since. We finally have a winner for the Cubane race. And the winner is... Cameolus. The mad lad just casually cooked the whole thing in between like it's not a big deal. And not just the dicarboxylic acid, no, the whole thing to the actual Cubane. But if we shift our attention to Australia, our favorite Australian chemist has, after 3 long years, finally produced some black tarry Cubane.
Let's go!
Oh, I'm sorry, that's actually not the cube, that's just benzophenone. It's kinda hard to tell all of that tar apart. In all fairness though, he is doing this whole thing with hardware store cans and has a PhD on the side. So, congratulations to both of them. In my last video on this project, we made the cyclopentanone ethylene Ketal, and in this one we will move all the way to the Diels order product. The first step will involve the bromination of the cyclopentanone ethylene Ketal to the tribromo compound, and in the second step we'll perform an elimination followed by a Diels order reaction to yield the endo-2,4-dibromo-dicyclopentadiene 1,8-dione bis-ethylene Ketal. And to avoid any strokes while reading this, I will simply refer to that compound as Bisketal. For the first part, we will need the cyclopentanone ethylene Ketal, 1,4-dioxane and bromine. But before we can start the synthesis, the dioxane has to be purified. This reaction is very dependent on reagent quality, and I really don't want to cry about the yield again. Since this dioxane was purchased from a chemical supplier, it is already quite pure and I can clean it with only sodium metal. The apparatus for this consists of a 3-neck round bottom flask, a large pressure equalizing addition funnel and a condenser on top. Into the flask I add about 600 ml of dioxane, which is a bit more than I'll need later, and I then bubble nitrogen through to remove any oxygen which might be dissolved in it. I let this bubble for about 15 minutes and then replace the pipette tip with a gas adapter. I also added a balloon on top so I can keep the whole system under nitrogen. Now I need to cut up some small sodium pieces. Sodium really is a fun metal. It is super soft and you can see I'm just cutting it with a spatula. I add the sodium into the flask and now I can just let this reflux until the solvent is pure and then close the stopcock to the funnel to collect it. The question of course is, how do you tell when the solvent is pure? Solvents usually aren't very talkative and staring at it for a long time also doesn't help. Therefore we will need an indicator. And the most common choice for this job is benzophenone. Benzophenone will react with sodium metal to form a ketal radical, which has a vibrant dark blue color. But this compound is quite unstable and is easily decomposed by oxygen, water and other impurities. Therefore, when the solution has a persistent dark blue color, the solvent is pure. The amount needed is also quite small and a few crystals are more than enough. Now all I have to do is let this reflux and watch until the solvent turns blue. Alright, now we have super pure dioxane and can finally start with the bromination. But first we have to safely dispose of the leftover sodium in the flask. Also, since we'll be working with bromine, the lab is temporarily moved outside in front of this beautiful brick wall. The setup is quite simple. The reaction vessel is a 2-liter 3-neck round bottom flask which is connected to a drying tube filled with calcium chloride and this inverse funnel gas scrubber, since we'll be producing a lot of hydrogen bromide. The gas scrubber is simply filled with some water, since I plan on recovering the HBr and concentrating it up to azeotropic hydrobromic acid. No need for that to go to waste. Recycling, yeah! Now I weigh out 128.17 grams of the cyclopentanone ethylene ketal and add that into the flask along with the dioxane that we just distilled, which is about 530 milliliters. The beauty of having all that in the addition funnel is that I can just place it on the flask and let it flow inside. Then I purge the reagents and apparatus with nitrogen for another 15 minutes. While that is happening, I start cooling down the contents in the flask with an ice bath, because the temperature in the following reaction should not rise above 5 degrees Celsius. And now comes the fun part. 511.39 grams of bromine are placed inside a large addition funnel on the flask. Working with this much bromine can be a big hazard, so precautions and PPE are extremely important. I have a bucket of sodium thiosulfate ready in case I spill anything, and I'm also wearing a respirator and thick gloves. The bromine has been triple distilled over potassium bromide and dried with phosphorus pentoxide to make sure it is free from water and chlorine. The ketal has also been redistilled before this preparation. Now I let the bromine slowly drip into the flask, and while past me has to just sit there and wait, let's quickly go over the reaction mechanism. There isn't much literature that I can follow here, but the amazing part of not being the first person to do something is that you can shamelessly plagiarize off of other people's work. So thank you to Chemiolis and that chemist who proposed the following mechanism for this reaction. First, bromine is hemolytically cleaved into two bromine radicals by light. One radical will then pull off a hydrogen from the ketal and form hydrogen bromide, and a radical form of the ketal which can react with another bromine radical to form a monobromo intermediate. The HBr can then act as an acid catalyst to convert the ethylene ketal into an enol ether. And this is where the dioxane comes into play. Dioxane forms a complex with bromine which polarizes the molecule, meaning that one bromine has a partial positive charge and the other one a partial negative charge. The enol ether can attack the positively polarized bromine and form an intermediate, which is deprotonated by the bromide ion left over, to reform another enol ether and more HBr. This process happens 2 more times until we are left with the tribromo ketal. As more bromines are added to the compound, it becomes consecutively harder to further brominate the molecule because of the strong -I effect of all those bromines. Additionally, we are limiting the amount of bromine available for reaction, so further bromination doesn't happen. Is this mechanism correct? Well, someone would have to further investigate to confirm that, but it's probably pretty close. The bromination proceeds fairly quickly as the solution decolorizes immediately after addition. This crystalline deposit on the walls of the flask is the dioxane-bromine complex, and especially on the addition funnel there's a lot of this compound. Now I need to carefully monitor the addition of the bromine to maintain the temperature below 5°C. Here we are again after the weekend, which means this stuff has now been stirring for 2 days. One should be enough, but I was busy with other stuff and longer reaction time doesn't hurt. The headspace in the apparatus is now completely filled with HBr, plus a whole lot more dissolved in the dioxane. So before proceeding and gassing myself, I will first flush all of the HBr into the gas trap with some nitrogen. The funnel trap sadly doesn't do that great of a job and lots of HBr is pushed out the side. In order to prevent that, I connect 2 gas washing bottles in series, which do the job much more efficiently. I purge the apparatus for 15 minutes, which should clear out most of the HBr, and afterwards I transfer the washing water into a canister so I can concentrate the acid later. An interesting thing to note is that the water has gotten noticeably warm. Dissolving HBr is exothermic, so I guess we collected a good amount. Now we can proceed to the next step in the synthesis, which is an elimination on the tribromo ketal, followed by a Diels-Alder reaction which forms the Bisketal. I won't isolate the tribromo Ketal though, and instead I will perform this step in situ with the crude reaction mix like the authors of the pilot scale paper. This saves me a full workup, and the yields of this procedure are equal to, if not higher than, the two-step synthesis. To do this, I first need to make a very concentrated solution of sodium hydroxide in methanol by first weighing out 222 grams of sodium hydroxide and then adding 1.1 liters of methanol. I made a small mistake here because I should have added the hydroxide to the methanol in portions instead of dumping everything in the beaker at once. I underestimated just how exothermic the dissolution would be, and the methanol started getting very hot. I really didn't want it to start boiling and spewing toxic methanol vapors around, so I stopped stirring for a moment and placed the beaker inside an ice bath to cool it down, and put a little dish on top to prevent any vapors from escaping. This worked really well, and the worst thing that happened were a few drops of condensate on the walls and the dish. Sodium hydroxide is moderately soluble in methanol, but it takes a whole damn lot of time to dissolve. I didn't time it exactly, but I was watching a 30-minute video on the side, and there were still little chunks floating around afterwards.
1 hour later.
Eventually everything dissolved and the solution has become very viscous and cloudy. It almost handles like syrup, but I wouldn't recommend eating it unless you want to know what pain tastes like. Unfortunately, my largest addition funnel is 500 milliliters, so I'll have to add the solution in portions. The temperature should again not exceed 5 degrees Celsius, so the flask is once again chilled with ice. At this point, it is also very helpful to have as little HBr in the solution as possible, because the sodium hydroxide will first neutralize any HBr left, which produces a whole lot of heat and would force me to run a marathon between the fridge and water bath to replenish the ice every 5 seconds. Getting all of the HBr out isn't necessary though, and would take way too much effort anyways. After everything is neutralized, the sodium hydroxide will then start reacting with the tribromo Ketal in an elimination reaction. Because the hydroxide is a strong base, it is able to deprotonate the Ketal and eliminate bromine under formation of a double bond. I will draw this as an E2 type elimination, meaning that formation of the double bond and elimination of the leaving group happen in a concerted step. But keep in mind that E1 might also be possible, which would form a carbocation intermediate on this carbon. The intermediate cycloalkene product will then undergo a second elimination and form this diene species. Interesting to note is that initial elimination on the monobrominated side is not observed. Furthermore, the first intermediate product forms much more readily at lower temperatures and is stable enough to be isolated. The second elimination is much slower and requires higher temperatures, plus the diene is much less stable and will immediately dimerize in a Diels-Alder reaction. A Diels-Alder reaction is a 4+2 cycloaddition which involves 4 carbons of a diene and 2 carbons of a dienophile that will react together to form a 6-membered ring. In our case, this intermediate will be both the diene and the dienophile. Diels-Alder reactions are very complex, but also super interesting because they are highly dependent on the orbital interactions of the reactants. I could spend hours explaining this reaction, but for the sake of this video, I will make the explanation fairly compact. This reaction is also much better to visualize in 3D space. The electron movement will be shown on the right. At first, 2 of our intermediate molecules will arrange on top of each other in a way that the p orbitals of the diene and the dienophile are able to interact with each other. The electrons will then move around in a circular motion and form 2 new bonds between the molecules, which will result in a 6-membered ring and a shift in one of the double bonds. This reaction is highly stereoselective, and the stereoisomer of our target molecule is only formed in a negligible amount. Removing it is therefore not necessary. The reason for the stereoselectivity is probably a combination of secondary orbital interactions and steric preference, since its transition state has the bromine and the acetal much closer to each other. Going back to the reaction itself, we can see that the dioxane has become a lot more opaque since I started adding the sodium hydroxide. This is due to precipitated sodium bromide, which is being formed as residual HBr is getting neutralized, and also as a byproduct of the elimination. As I add more of the sodium hydroxide solution, I noticed that the stir bar is having a lot of trouble stirring the reaction mixture. I mean, there's almost 1 liter of liquid in this flask and a lot of precipitated solid, so it's holding up valiantly, but I'm pretty sure that with further progression it will fail eventually. So I decided to give the stir bar a break and instead use my KPG stirrer for this reaction. With this powerhouse installed, the stirring immediately gets better and we don't have to worry about our stir bar getting stuck. After about 4 hours, all of the sodium hydroxide has been added, and as you can see, the reaction has turned from a bright yellow color to just black with some solids at the bottom. All of this powder is sodium bromide with maybe some sodium hydroxide mixed in it. The black color probably originates from the Bisketal in solution. To push the reaction to completion, this solution now has to be refluxed for about 18 hours. But since there's no more gas being produced, we can now move back into my trusted lab. The reflux has now been completed, although I didn't heat it for 18 hours consecutively, but instead in 3 6-hour increments. I do need sleep and stuff. Optically, nothing really changed. It's still black, but now hopefully saturated with juicy product. Now we just have to isolate it. And to do that, we can take advantage of the fact that every component in our reaction mix is soluble in water, except for the product. Because my beaker size is limited to 2 liters, I'll have to do this in multiple steps, where I add about half a liter of reaction mix into 1 liter of ice water. Immediately upon addition, there's a beige precipitate forming in the beaker. The precipitate is then filtered off, and the filtrate is once again completely black. I will now quickly dispose of the filtrate, and then we can filter the rest of our product. And now rinse and repeat with the remaining solution. The flask also gets a cleaning, of course, and with this filtration we have processed all of the reaction mix. Everything remaining in the filter should be product. The filter is quite full, but as you know, I like to push the limits with my glassware. To get the product nice and clean, I wash it with a bunch of water, but because the frit is so full, it's a little hard to mix everything through. So I just dump it into a large beaker, and then really get that water in there to pull all of that filth out.
You dirty boy.
And after filtering everything again, we do 3 more washings with ice-cold methanol straight out of the freezer. Now we can scrape everything into a large petri dish. It's still a bit brown, but that's just from residual solvent. After fully drying the product, it has a very nice light beige color. If you would recrystallize it, it would be completely colorless, but I'm not gonna do that. I had an NMR taken of the product and it's already very clean. Also, further processing works completely fine with the crude. I also tried to isolate some more product from the methanol washings by diluting it with water, and some stuff did precipitate, but most of it was too fine for my frit, and everything I managed to collect was some weird sticky brown tar. I don't know if there's any product in there, but it's definitely not worth the pain to find out. The final amount of product is 157.62 grams, which is a yield of 77.63%. That is a beautiful yield, and it's also only 2.5% lower than the paper. And with that, we are done. The next step is going to be building a photoreactor, and then we can finally finish up with cubane. At this point, I would also like to thank all of you for supporting my channel. I really didn't expect it to grow this fast. And of course, also a big thank you to my patrons. You know, you could also be on that list, huh? Wink wink. Anyways, that's it for 2023. I'll see you again the next year with many exciting projects. Until then, I wish you all a pleasant time and stay tuned.